Hello and welcome to another episode of TWiML Talk, the podcast where I interview interesting people doing interesting things in machine learning and artificial intelligence. I'm your host, Sam Charrington. In today's episode, we're joined by Kamyar Azizzadenesheli, PhD student at the University of California, Irvine, and visiting researcher at Caltech, where he works with Anima Anandkumar, who you might remember from TWiML Talk 142. We begin with a reinforcement learning primer of sorts, in which we review the core elements of RL, along with quite a few examples to help newcomers get up to speed. We then discuss a pair of Kamyar's recent RL-related papers, Efficient Exploration through Bayesian Deep Q-Networks, and Sample-Efficient Deep RL with Generative Adversarial Tree Search. In addition to discussing Kamyar's work, we also chat a bit about the general landscape of reinforcement learning research today. So, whether you're new to the field or want to dive into cutting-edge reinforcement learning research with us, this podcast is here for you. If you'd like to jump ahead to the research discussion, the primer portion of this show is about 30 minutes long. We'll have a more specific timestamp noted in the show's description, so check your podcast app or the show notes at twimlai.com/talk/177 for that. A quick note before we get into the show. Monday is Labor Day here in the States, and we won't be publishing a show then. But this is an extra long episode, which should tide you over until we do publish the next show, which will be Thursday, September 6th. All right, on to the show. All right, everyone. I am on the line with Kamyar Azizzadenesheli. Kamyar is a PhD student at the University of California, Irvine, as well as a visiting student researcher at Caltech, where he works with Anima Anandkumar, who was a guest of ours back in May of this year. Kamyar, welcome to This Week in Machine Learning and AI.
Yeah, thank you, Sam. Thank you for the introduction.
Why don't you give us a sense of your research interests and some of the work you're doing at Caltech and Irvine?
Great. My research interest is mainly in area of like a specific area of machine learning, which is called reinforcement learning. This is my main focus on my main research interest, but at the same time, I do a lot of other stuff in the field, like tensor methods. I do optimization. I do generative models, study of generative models. I do a study of like safety and fairness in machine learning, because we build up many theory in machine learning, and we build up many practical, like revolutionary methods. But the question is, can we use them in real world? And then the answer is like, hey, you need to make sure that your algorithm is robust, your algorithm is like safe, it's like fair. There are a lot of questions you can ask when you take your machine learning algorithm and deploy it in real world. So those are another part of like machine learning field that I'm interested in.
And we've talked about reinforcement learning on this podcast a number of times, both from a theoretical perspective as well as applications like game playing, AlphaGo, things like that. But for this conversation, I thought we would dig into a couple of recent papers of yours looking at deep reinforcement learning, but also spend some time up front to refresh ourselves on some of the foundational research in this area. So why don't we get started by having you kind of walk us through some of the core elements of reinforcement learning, like Deep Q-Networks, for example.
Great. That's amazing. I really like to, whenever I want to talk about and explain like reinforcement learning, I get super excited because it's like amazing framework and amazing setting that almost, it has like a lot of intuition from human behavior, and also it has super nice theoretical analysis, and the modeling is crazily great, and I really love it, and I really like to explain to others. It's like let's assume that I can give you one example. Let's assume that you have a vacuum cleaner in your house and or your apartment, your place, and you just leave it alone, and this vacuum cleaner should know how to clean your place. So what it does is vacuum cleaner goes around. If it finds something and if it's cleans that place, when you come back home, you tell the vacuum cleaner, hey, you did a good job. And if you the other day, if you come back home and you see the vacuum cleaner didn't do anything, you tell the vacuum cleaner, hey, you didn't do a good job. It's you punish it. I'm not you do not punish it, but it's this is a term we use. So you give some sort of reinforced feedback to the robot or to the agent is going around the environment. Or let's say even make it easier and which might make more sense is a baby, a newborn baby. If the newborn baby is getting closer to to fire, the baby feels some harm, and also parents tells baby that hey, do not do it. Or if baby does something good, parents they give the baby a reward, which is let's say candy, hopefully not candy, but something rewarding to the baby, and baby learns that the thing that he or she did was good thing. So over time, the baby interacts with the environment, which is the whole world and parents, and based on the decision the baby makes, going toward the fire or getting higher grade in school, or I don't know, learning how to when let's say assume I'm father of a baby and I'm teaching my baby how to ride a bike. If my baby does a good job, I give a lot of rewards. So my baby is my kid is has this incentive to learn this task faster. So it's the baby here or the kid here is the RL agent. It's interacting with the environment, and based on these signals, these feedbacks it receives, learns how to do a best job and finds the optimal behavior. So it's a general framework why I really like reinforcement learning, because it's almost all the time we have reinforcement learning problems because we are learning. Human runs reinforcement learning somehow. It's not a exact statement, but somehow you can think of it. So reinforcement learning is actually, or in short we call it RL, is actually really interesting framework that it has a lot of root in psychology, a lot of root in neuroscience, and also theoretically we found it from graph theory, which was quite interesting. So from theory we analyzed many things, and at some point we realized that is actually the way human behaves. So it was the nice intersection between psychology and neuroscience and machine learning, which was quite interesting. So so this is a motivation why reinforcement learning is important and why we work on reinforcement learning. Because if we can understand the way human learns and the way mathematically we can make system to learn, then we can design a robot which can clean a house, or which can I can build a robot arm which helps me to build something, or grasp something, or if I do not have leg, it can help me to walk. Or I can come up with a robot which can help my doctor, and my robot is given a patient comes to my clinic, I ask doctor, hey, what is the best prescription you can give to the patient? And also I ask the robot, hey, what do you think? And the robot has seen many other trials over the world. So the doctor cannot see all the possible experiences that all other doctors they have seen. But if I can have a robot which interacts with all the doctors around the world, and I give that robot to my doctor, and my doctor can see what my robot thinks and what my doctor, his own or her own, is thinking about that new patient, and then combine these two information and give the better prescription to the patient, and patient gets better over time. So there are a lot of interesting application and necessary and interesting application of reinforcement learning in in real world. So, but the way we model it is, there are many ways to model and this setting. I just want to talk about one of them because it's mostly used in deep reinforcement learning. Let's assume I'm playing a game, okay? When I play a game, let's say, I don't know, you're familiar with, let's say, GTA, okay? And
Grand
when I
Theft
play,
Auto.
yeah, Grand Theft Auto. Or, yeah, this is one example that I can imagine many people have seen it, because either they were like punishing their kids for playing this game like for 24 hours a day, or the kids, they play it themselves. Is like you have this agent going around the world, its own world, and like needs to make a decision to optimize its final goal. Okay, so the decision the agent makes at each point is like walking to left or right, or like going to the barber shop, this or going to gym, this kind of stuff. These decisions at the time gives it like some reward. Each of these decisions has like long term effect. If my like guy in Grand Theft Auto goes to like gym, it gains more power, can run faster. Okay, so this running faster doesn't have a meaning at the time, but the thing is, this running faster feature is useful for the agent for later, in like few days later, when the agent is going to run away from the cops, something like that. So the action you're making, the decision you're making now has long-term effect. It that effect of this like action is like appears like later. Let's say if I'm like sitting in my office, I'm gonna grab a coffee. If I grab my wallet now, it doesn't have any meaning until I get to the coffee shop and I want to pay. Okay, the action I made at the very beginning has a long-term effect. Or if like I want to invest in a bank, the bank tells me like, hey, if you put money now, you're gonna get return like over years. So the action I'm gonna make has like reward, and this reward is like accumulating over the whole future. So it's like this reinforcement learning has this temporal like effect. Like if I make some decision now, I see the effect of this decision like way later in the future, which is like makes the problem hard and also makes the problem interesting, because real world works like this. If I break my arm now, I might have serious problem like the whole life, like the rest of my life. It's not just I see something kind at that time step. I see same thing like that effect for lungs.
And so one of the big challenges in reinforcement learning is the idea that you've got this huge, in many cases, environment. Like if we're thinking about the analogy to humans, you've got the entire world of things that you can do. And so how do we decide how we explore all of these possible actions and states that we could end up in?
Yeah, that's actually amazing question, and it's the challenge for reinforcement learning that we are trying to deal with like for many years. Is like, so now I give you the world, and you need to explore this world. You don't know what each action is doing. So, and you don't know if you follow some sequence of actions where you're gonna end up. So that's exactly the interesting question that you need to explore. Let's say you go to coffee shop. I'm bringing this example of coffee shop. I don't know, like so it makes it more interesting. You go to coffee shop, and there is like latte. You have like, let's say, 5 options. There is latte, there is americano, there is like cappuccino and brewed coffee, and also let's assume that in your local coffee shop they also sell vodka. And you go to like coffee shop in 8 in the morning. Let's assume that you are not Russian or like Polish, and you go 8 in the morning to the coffee shop and you want to get coffee. You for sure not gonna order like vodka, right? But you don't know that you like latte the most or you like cappuccino the most. What you do, you need to know which one you think is the best one now, and like you drink. Let's say you choose latte, but tomorrow when you go, you're like, I don't know what is the taste of like cappuccino. Let's try cappuccino. And you, for the first time, you try the cappuccino for first time. Third time you go, you order maybe brewed coffee. And the fourth time you go, you're like, okay, I think latte was good, so I'm gonna go with latte today. So you get latte, and the day after you say, well, I'm not pretty sure how like cappuccino tastes compared to latte. So next time you try like cappuccino. So over time you do this type of exploration. You are trying different things, but you do not try vodka. So you try some actions that they make most sense, right? So this is the way we want the RL agent or robots to do exploration. We don't want to have a RL agent to explore everything uniformly, which is not possible. I don't want to have a GTA or Grand Theft Auto like agent to just go left, left, right, right, like without any reasoning of like what it does. I want to have the agent which does exploration in such a way that it maximizes the amount of information it gains from the environment while trying to, by information, it can build better understanding of the world while do not forgetting that the agent is there to collect like more like rewards. It's like those money in Grand Theft Auto game. So my agent wants to, my GTA agent wants to go around and understand how the world works while it wants to maximize the understanding of the world or minimize the uncertainty around the world while trying to maximize the reward of the game, maximize the score of the game, or like get the game to be done. If you have a kid playing like GTA, the kid doesn't explore the whole year and then start playing games. The agent, while playing games, like try to learn and build a model and see who is friend, what is good, going to gym is good. At the very beginning, the kid might not know that going to gym is good. Maybe if you go there, they kill you. So something like that. So there are a lot of things, characteristics of the environment that you need to learn, you need to explore, but you need to explore it carefully. So this, the way you do exploration is like actually the key factor in reinforcement learning that most of my works are based on, like how to do exploration efficiently.
And so one of the simple concepts that comes up in reinforcement learning is this idea of explore, exploit, and you've talked a little bit about that trade-off, via examples. And then one of the algorithms that encodes that is this idea of Epsilon Greedy. What is that?
Epsilon Greedy is actually a super powerful and interesting like algorithm, and it's super simple as well. What it does is like, again, I'm going to talk about coffee shop. You're at a coffee shop, you have these 5 options like I told you. You have latte, cappuccino, Americano, and like brewed coffee and vodka. Okay? So now let's assume that so far based on let's assume that you have been in the coffee shop for many times and you know that you feel that you are a fan of latte the most. You like the latte the most. So your greedy decision, which is like the decision which maximizes your satisfaction, is choosing latte. Okay, so Epsilon Greedy exploration and exploitation strategy says, hey, with probability, like let's assume epsilon is like 0.1. It says with probability 1 minus 0.1, which is like 1 minus epsilon, I'm gonna choose the most greedy decision which maximizes my satisfaction, which is latte. So with probability 90%, I'm gonna choose latte. And also I say, hey, I'm also not pretty sure about other decisions. I'm not very sure about like cappuccino. So what it does with probability 1 minus epsilon, which is like 10%, the agent randomizes over all these 5 actions. Okay, so it's like with probability, but with probably 10% it randomizes over all the actions. It means that sometimes it's like choosing cappuccino, sometimes choosing Americano, and sometimes choosing latte when it does exploration. And also it sometimes chooses vodka. So it's like the probability that you choose vodka is exactly equal to the probability that you choose brewed coffee or like cappuccino, which is actually the part that Epsilon Greedy fails, because you know that vodka is not good. Why you choose it again and again? So this is one part that in one of my papers we address and we resolve this issue, which is quite interesting. So Epsilon Greedy is a powerful algorithm. It does choose like the best action with high probability. The best action, the best action that agent so far knows is the best, might not be the best. And with probability 1 minus epsilon, with probability epsilon is gonna just uniformly choose other actions, even though the agent might know that some actions are really bad, but it does choose them. So this is the Epsilon Greedy, and it's been used in like area of deep. It was a prominent like algorithm for making trade-off between exploration and exploitation in area of deep reinforcement learning. And one of the famous algorithm which uses this is Deep Q-Network. So I can just briefly tell like what Deep Q-Network does is, so let's go back again to the Grand Theft Auto game.
Deep Q-Networks are one of the algorithms for deep reinforcement learning that really popularized the space and launched a lot of the efforts to solve video games and things like that. It was created at DeepMind, is that right?
Yeah, Deep Q-Network was created at DeepMind, and it was like one of the main reasons why like there are many researchers are working on deep reinforcement learning, because this first paper made it somehow possible to go beyond like a small grid work, small games that theoreticians we were like working on the small words. And like this paper was the first paper that we were able to apply reinforcement learning methods on the games like Atari's and like the video games, the games that we were not even thinking that it's possible to solve using reinforcement learning algorithm at the time. But this paper was like a kind of revolutionary paper that brought a lot of attention to the field of reinforcement learning, and people start working on this field. As a lot of practitioners and like scientists, they start working on these games and on these algorithms, because this first paper made it somehow. It's not. I'm not claiming that it was like the huge gap between the previous works and this work. There were like many works before, like Deep Q-Network. They were able to do many things on Atari games, but this one was the simplest one, which had like simple idea and deployed neural networks in order to solve Atari games. So it was like quite interesting.
And so what's the relationship between Epsilon Greedy and Deep Q-Networks?
So the way Deep Q-Network works is like, let's get back to the Grand Theft Auto. The agent walks around the city, and for each action, it knows that if the agent chooses that, let's say, action going forward or shooting that person, it has the follow-up return. Like if it does something, it might win the game, or like it might get some reward or some money, some score. So each action has like upcoming and like forwarding reward. So it's like each action has value. How good is that action? If I kill that person, so sorry for my language, but if I go to the gym, how much value it has for me? How much I get fulfilled if I do this action now? So what Deep Q-Network does for when it plays game is like, given the state of the game, even given the image of the game, which is like the frame of the game, it decides how good is each action. It's like computes the value of each action. Okay. For example, if I play Sequest, which is like a submarine, is like in the sea, is getting out of oxygen, needs to go on the top of the sea and like get some oxygen. If I see I'm running out of oxygen, I know that going up has the most value for me. It's like and staying around the bottom of the sea has lowest value. So what Deep Q-Network does, Deep Q-Network finds the value associated with each action. Okay, the way it constructs this value, is like the agent needs to interact with the environment. The way the agent interacts with the environment to collect samples and explore the environment is Epsilon Greedy. So what Deep Q-Network does, builds a model which somehow gives the value of each decision, and with probability like 1 minus epsilon, it goes with the best decision the agent so far thinks is the best, and with probability epsilon, it randomizes over all the actions. Okay, so if I run Deep Q-Network on myself when I go to the coffee shop, with probability 1 minus epsilon, I'm gonna choose latte, and with probability epsilon, I'm gonna randomize over all the actions. Okay, so this is like the way Deep Q-Network works. It learns how good is each action. It learns the value associated with each action. How good is making the like action up at the current time step? How good is this action? So it learns this function, And when it learns the way it learns this function is like collect samples to learn this function better and better.
And so we can think of deep Q networks as essentially an algorithm for accounting for the various values of these actions over a series of steps. Is that fair?
It's fair. It's fair that it's like counting the amount of reward it's gonna receive in the future, and like somehow instead of memorizing all of them, it learns a function which like approximate this count.
Mm-hmm. And so,
in the best case, there are many theoretical analysis which show that it doesn't do it exactly, but we can for this conversation we can assume that it does.
Does deep Q networks specify a particular type of neural network architecture, or can it be implemented with multiple different types of networks?
Oh, deep Q network is actually an algorithm, and it can be used anyone can design his or her own, like our neural network architecture. Neural network here are like the machinery we use to solve this problem. But deep Q network its own is a generic algorithm. It doesn't care that you're using neural network, you're using kernel machine, or using linear models. I mean, the objective is being used there is generic and can be applied on the variety of different models and can be applied on a variety of different architectures. But the first paper used this objective function on using like deep neural networks. So that's why we call it deep Q network.
Mm-hmm.
So the thing is like it can be applied on any architecture designed for like deep networks. I can design my own deep net. I design also like for different tasks. I design different neural network architectures, but I still use deep Q network like machinery and algorithm to optimize and learn this value of each decision.
Okay.
So it's kind of generic algorithm. It's not just for a specific neural network. It's like it works. It's generic and it's applicable to a variety of almost all the neural networks.
Are there specific neural networks that folks tend to use with deep Q networks?
Yeah, for Atari games, when we are like dealing with Atari games, we are using a specific neural network. Mainly, people have tried different neural networks, but mainly we use the same neural networks that DeepMind paper back in the day, not back in like a few years ago, developed. I mean, nowadays, like the time is when you say back in the day, you mean like 5 years ago in the field of AI. But yeah, so far, like most of the researchers, they use the architecture designed in the original deep Q network paper, which is like interesting because we use the same architecture and we design better and better algorithms on the top of deep Q network. So we have variety of extension to deep Q network. We have double deep Q network. We have my work, which is like Bayesian Deep Q network. It's like we use the same architecture, but we are developing better and better algorithms.
And once again, what makes an algorithm better and better in this context is its ability to make better decisions about what elements of the space to explore or what decisions to make at any particular juncture so that it's more sample efficient. That's a concept that comes up a lot in here. How efficiently are we using our time in the environment to train an algorithm?
That's a super interesting point that you brought up. Is I want to learn the optimal behavior for, let's say, playing game in minimum number of interaction with the game, right? I don't want to like play game for 25 billion years in order to like by game I mean the simple, let's say game Pong or game sequence. I don't want to play this game for like 25 billion years in order to be able to, by years I mean like time for the Atari games. So I don't want to play that. I want to like play these games for like, I don't know, half an hour. By hour, I mean, this time I'm talking is like a time that actually you need to play that game. It's not like the time that you're RL agent is going to use. It's going to be the number of interaction with the environment you have. You don't want to have the number of times you play the game. You don't want to be like 20 billion in order to solve the game. You want to play this game 100 times and be able to learn it. Or you want to play this game like 200 times and being able to learn. So the sample complexity is really issue in reinforcement learning, and the goal mainly is to design an algorithm which makes the optimal balance between exploration and exploitation and minimize the sample complexity, or some other notions that we call regret, which is like you don't want to lose a lot before getting to the good performance.
And another thing is that these environments, they can effectively have like, local optima, meaning you could, going back to your Starbucks coffee shop example, you can kind of get into a rut where you settle on the latte and that's what you choose. But, you don't know that in one particular day, you happen to order the cappuccino, the person behind you also orders the cappuccino, and you find out that you're soulmates and like we're destined to be together. And if you didn't order the cappuccino, you would have never have had that experience. Like the games, these environments are so dynamic that unless you're really careful about the way that you explore them, you miss opportunities.
Yeah, it's like you're totally right. It's like these environments are super complicated, and like the dynamic is like weirdly complicated, and that's a part that makes our life really hard and also interesting. So like if the setting might have a lot of weird and complicated situation, and it makes me to explore all of them. Okay, but if I'm gonna, for the first time I go to coffee shop, I don't care that much that there is a person behind me is gonna be my soulmate. But if I go to coffee shop and I learn that which coffee actually I like, then when I'm certain, then I start to explore other stuff. I see who is behind me. So for example, first time I came to the United States, I was not able to speak English very well. So when I went to coffee shop, I was like just focused to get my coffee and pronounce things correctly, and like say my name correctly and be ever and pay correctly. But nowadays when I go to coffee shop, I just while ordering coffee, I talk to the person behind me. Okay, so over time, when I get more confident about the state of the environment, the way I need to make a decision, I start to do more complicated exploration. So it's like the way human does. And I was like, when I first came to the United States as a person who was not speaking English before coming here, so I had this experience that when I start going to coffee shops, I was not even care who is behind me. I was just focused to talk to the lady or the person, the guy there, and just make my mission accomplished. I wanted to just order my coffee and make that task done correctly.
And so you've got these two different metrics for what makes a good algorithm. One is its sample complexity, sample efficiency. The other is the degree to which it fully explores the environment.
There are many terms, but for simplicity, let's call it like sample complexity, like how many samples I need to come up with a good strategy.
Okay, so in other words, what I'm hearing you say is you can kind of boil all of that stuff down into sample complexity at the end of the day, whether it's, it's the algorithmic, like the computational element of it, whether it takes a long time to converge on anything or not, whether it takes a long time to figure everything out or not, but all of this stuff is ultimately related to the sample complexity.
Yeah, all of them are happening. Like the goodness of the sample in the sense that I get lower uncertainty about my world, and also how much that knowing that sample is going to help me to come up with a better strategy or better decision. This combination drives me to come up with the sample complexity.
And so with all that in mind, maybe you can walk us through a couple of your papers on this topic. One of them is the one that you mentioned earlier, the Bayesian Deep Q-Networks. What are you trying to do there?
Yeah, the Bayesian Deep Q-Network is actually quite interesting. I really like that work. It has some theoretical guarantee about the sample complexity, but also it has interesting behavior in real on Atari games. Let's go back again on the coffee shop example. Epsilon Greedy, what we're saying is like, is gonna choose latte with high probability and randomize over all the actions, all the other decisions uniformly, right? So Epsilon Greedy is also gonna choose the vodka with same number of times that it's choosing other like cappuccino or brewed coffee. But the thing is, what is happening is like, it doesn't care that how confident you are about the other action. It just cares how much information you know about the best decision, which is like latte. Okay, so even for Deep Q network is like computing the value of each action. If the action related to the vodka, it has a really low value, the epsilon greedy action is gonna choose that. Okay, so what we do in Deep Q network, we say, hey, instead of just estimating the by yeah, we do it in Bayesian Deep Q-Network is we are saying that instead of estimating the value of each action, how good is each action, also estimate how confident you are about the value of that action. Let's say I'm really confident that the value of like the latte is like high, but let's say I'm not confident that the value of the cappuccino is high. So I have estimation of the value of the cappuccino. I know how cappuccinos should be good, and I also know that I'm not that certain. Okay, so it's worth trying. So if I know that the value of the cappuccino is like high, but it's not as high as latte, but I'm really uncertain about this value, like how good is the cappuccino, then I would like to try it, right?
Mm-hmm.
And also, if I know the value of the vodka is really low, and also I know that with high confidence, I know that the value of vodka is low, I'm not gonna ever like try it, right?
Right.
So what Bayesian Deep Q Network does, Bayesian Deep Q Network is like an algorithm on the top of Deep Q Network, but it says instead of estimating just the value of each action, also estimate how confident you are about each action. And when you want to make a decision, see how good is the value of that action and how much you're confident. And if you're not confident about the action with high value, let's try that one. Okay, so it's like what it does is like the exploration doesn't happen in epsilon greedy setting. The exploration happens in a setting that it tries to maximize a combination of the uncertainty and the expected like goodness of that action. If the action the agent thinks is good, but the agent is certain about that, but there's another action which is slightly worse, but you're really uncertain about it, you want to try that one. Let's put it this way: you go to a coffee shop, you always get latte, and you never got like cappuccino, but your grandma every day talks about cappuccino. Okay, when you go to coffee shop, you believe that the cappuccino has high value because your grandma is always talking about it, but you never tried it, so you have a gigantic uncertainty about it. Okay, but still you love latte. So at this situation, you better to choose like the cappuccino because you think is a really good drink, is not as good as latte you think, but you're not sure that how good it is. Maybe it's way better than latte, but you don't know. Okay, but in expectation, the way your grandma explained it to you, you think that it's a good drink. It's comparable to latte, but it's still you like latte a bit more but based on your grandma's like explanation, you don't know that cappuccino is how good it is, but you roughly speaking, you know that it's not. You believe that it's not better than latte, but you are not certain about it. So you just try that one. So it's like kind of a balance between like uncertainty over your belief about the value of each decision, and makes a decision based on the expected value of each action and also uncertainty over that expected value.
And so are you, in the epsilon greedy, you are choosing your primary, the one that you believe has the most value at a probability of 1 minus epsilon, and then say you've got your 5 choices, the probability of you choosing one of those other ones is epsilon over 4, right?
Yeah,
and
it's over 5.
Epsilon over
5. I randomize over the whole thing.
Oh, you randomize over the whole thing. And so that was my question with the approach we're describing, where weighting, are you are you doing this confidence weighting over just the other four,
No.
or over all of
All of them?
You're just kind of evaluating each of them based on this confidence weighted metric.
Exactly. So for each action, I have estimated value, and also I have uncertainty. And what I do, so somehow it's like I have a belief about each action.
Mm-hmm.
Okay, I know how good it's gonna be, but this goodness is not a number. It's like somehow a distribution over each action. So I'm like, when I say I believe that this should be okay, it means that with high probability, I think it's good, right? So for each action, I have a distribution about how good each action it is. And the mean of this distribution is going to be my expected value. And also this distribution has some variance, is going to be somehow my uncertainty. Okay, so for each action, I have a belief, and my belief is somehow a distribution over the goodness of each action, or is going to be uncertainty over each action.
And thinking about it in terms of distributions is where the concept of Bayesian comes into play.
Exactly. So this distribution is like my belief, my posterior belief about each action. So if I know the posterior belief about each action, what I can do for each action, I can sample out of this belief. I get some let's assume that for latte, my expected value is like 5, and my variance is like 1. It's like I'm somehow uncertain that it's between 4 to 6. Okay.
Mm-hmm.
So what I do, I sample a number between 4 and 6, and I assume that the value of the latte is that number. I do the same thing for other actions. Like for latte, I know that my grandma told me the value of the latte. Sorry, for cappuccino, my grandma told me the value of the cappuccino is like 4. But I'm like, my uncertainty is like the variance of.
Well, she thinks it's higher than the latte, so maybe like 8.
No. She tells me that the cappuccino is good, but for me, she thinks the cappuccino is the best. But for me, I think the latte is the best.
Okay.
So for me, cappuccino is like 4. I never tried it. My grandma told me. I put 4 for cappuccino, but the variance for cappuccino is like 10. So the cappuccino can be between 14 to minus 6. Okay.
Got it.
So if I sample, there is a high chance that the cappuccino is gonna get a number above like 5. If the cappuccino gets a number above 5, above 6, I'm gonna choose cappuccino.
Mm-hmm.
So this is the way I do exploration. This is called Thompson Sampling. There was a guy back in 1930s, and he developed this idea of sampling. If you have a belief about the environment, you sample out of that and just act based on that sample. Also in psychology, there's a literature they do not call it Thompson sampling, they call it Bayesian sampling, because they are from psychology background, so they define their own terms. But they have a cool setting that they say even human. That's why I bring up this coffee shop example. Is like they say in psychology that human also does Bayesian sampling. The human come up with a belief about the world, belief about each decision, and sample out of that belief and do the human thing. It's like the human randomizes over its behavior.
Mm.
Doesn't go always with greedy. We do not always get a latte. We sometimes randomize. The way we do randomization is sampling through our belief. I mean, this is a claim in psychology. I'm not making this claim.
Right.
I'm just repeating the thing they say.
I'm not sure how exactly to articulate this, but it strikes me that there's, one of the important assumptions in here is this idea that, I guess the whole idea of sampling, right? That you can just pick a number, and even though relative to the distribution, that number could be an extreme outlier, we're still just going to use this number to make our decision. Like what tells us that we can do that?
So that's an interesting question. So if I draw samples and one sample is extremely high, and the question is, should I go with that? or not. So,
and so I guess maybe to start to answer my own question, are we just kind of reverting to law of large numbers here? If we do this enough, we're basically sampling around, we'll kind of converge to our distribution?
it's slightly related to that, but it's not exactly that. Here, it's about concentration of the measure mainly. It's like if I have an uncertainty about the latte and cappuccino and others, if I sample them a lot, then I am gonna be sure how good they are, right?
Mm-hmm.
If I'm, let's say, in the not realistic world, I'm able to drink latte 10 billion times, and I'm allowed to drink cappuccino 10 billion times. Then I can say which one is better,
mm-hmm.
right? So it's like over time, my belief concentrates over its actual value.
Mm-hmm.
Because latte for me has a goodness. I don't know what is that goodness, and I need to try it many, many times to understand what is that goodness. And if you allow me to drink latte billions of times, then I can, over time, I can like shrink down my uncertainty about latte, and at some point I say, hey, latte is actually the best, even though it might not be. But for other people, for me, let's say, is like when I drink latte a lot and cappuccino a lot, over time I am certain about which one is good.
So it's not just law of large numbers, because we're not just sampling a lot from this distribution to learn its parameters. We're also updating the distribution, the parameters of the distribution, as we go along to reflect our increased confidence.
Yeah, and here is like the distribution. So my belief is my distribution, right? So this distribution at the very beginning has a like fat tail. But over time, when I collect more samples, I'm gonna make sure that. So what is this distribution? This is a distribution over the value of latte, right?
Right.
So the value of latte in expectation is a fixed number. So it's 5, right? So, but I'm not sure about it. So I am uncertain. So this distribution represents my uncertainty. And over time, when I collect more samples, I'm reducing my uncertainty, and this uncertainty is gonna be shrink down. And over time, if you allow me to collect more samples, I'm gonna shrink down my uncertainty to 0 and claim that I exactly know what is the value of the latte.
Mm-hmm.
So it's gonna be like a measure of uncertainty. Like if I get more experience, if I try same thing many times, I get more certain about it. It means that I reduce somehow the variance of my belief about that action
mm-hmm.
or that decision. So it's gonna reduce that the uncertainty over the world for me. So and it's been like studied that if you use Thompson sampling, you actually nicely balance between exploration and exploitation, and you actually get a order optimal sample complexity.
So a part of your work then is applying this Thompson sampling algorithm to deep Q-networks, and does the analytical results follow as well into the reinforcement learning realm?
Yeah, it does. I'm not applying Thompson sampling on deep Q-network. I'm extending deep Q-networks to have this Bayesian property. Deep Q-networks, they, as I said, they just compute the value of each action. But Bayesian Deep Q-network use the same machinery as deep Q-networks, but instead of computing the value of each action, it also not only estimate the value of each action, it also estimate the uncertainty of that value. So it's like collecting more information.
Right.
And on the other hand, for exploration, Bayesian Deep Q-network doesn't use Epsilon Greedy, but it uses Thompson sampling,
mm-hmm.
which is like super interesting. I mean, the first time I applied this algorithm, this method on the Atari games, it was like when I was showing this result to my colleagues, no one was like believing that what's going on, because it was doing super great, like 1,000 times better in the performance, like 100 times better in sample complexity. It was like crazily good. It can learn the game that deep Q-network learns in 100 million times. That it can learn it like less than 5 million or less than 2 million for some games. It's crazily cool. It was like interesting observation and made us to think more about exploration. If you look at the literatures in the deep reinforcement learning, almost like more than 99% of them, they use Epsilon Greedy. There are few of them they are using more sophisticated exploration algorithm. And here we show that if you just, instead of doing architecture design, if you just come up with better exploration strategy, you're gonna gain a lot.
Has that result stood the test of time? Is this still state of the art for certain games, or has it been extended by other folks? Like, where does it sit in the landscape of extensions to Deep Q-Networks?
Oh, interesting. That's an interesting question. It's like after Deep Q-Network, there have been many extensions to design better cost function, to design better like sampling, to design better handling of the memory. There are a lot of extensions that they advance Deep Q-Network, okay? Mm-hmm. But they almost all using Epsilon Greedy, okay?
Right.
So we are not comparing against those advanced architecture. We are just saying, just take the simple Deep Q-Network and instead of doing Epsilon Greedy, do Thompson Sampling. And we show that it does way better. And also we show that it does better than many other algorithms, many advanced algorithms. Mm-hmm. But we did not compare against those algorithms that they are advancing the architecture or advancing some other like rewarding functions. Because the point of this work was like, hey, if we just change the exploration algorithm, what's going to happen? If those algorithms that are advancing Deep Q-Network, if I apply this Thompson sampling on those algorithms, I'm gonna get like better performance.
Got it. So you kind of left it as an exercise to the reader to take their favorite extension to Deep Q-Networks and try this as a way to get even better sample complexity.
Yeah, it's like this is like the way we say to do exploration and exploitation instead of Epsilon Greedy. If you have a sophisticated like deep reinforcement learning algorithm, if you're still using Epsilon Greedy, if you apply this approach, which has a theoretical like analysis and also theoretical guarantee, you hope to get way better performance.
What you've done here is you've proposed an alternative to Epsilon Greedy based on Thompson sampling, so based on uncertainty weighting. Presumably there are, other ways that you could change the explore-exploit mechanism further. How well explored is that space? Have a lot of people proposed different algorithms for dealing with exploitation?
That's a super interesting question. Is from land of theory, the main question we are asking almost every day is to come up with the better exploration and exploitation algorithm. From the theory land, we developed a lot of nice, amazing, and sweet, I would say, algorithms. They balance this exploration and exploitation for different settings. Okay, so theoretically, this area is nicely studied. There are a lot of rooms to explore more and like to prove and like study new things and like find the optimal way of exploration. But the thing is, extending those methods. Even I have a few like theoretical way of doing exploration and exploitation in the theory land, but it's not easy to extend those ideas and those settings to deep neural networks. Okay, so from the theory we have a lot of algorithms and we have a massive amount of studies that we know how to do exploration and exploitation to get some sort of order optimal like sample complexity. But the problem is like those algorithms are not easily extendable to deep reinforcement learning.
Is it simple to explain or give an example of an algorithm that isn't easy to apply, or how or why they tend to break?
So one of the major portion of the theory land in reinforcement learning is like model-based reinforcement learning. What we do is like we literally learn we literally learn the model dynamics. Okay, for each state we store the transition from each state to another state. Okay, if I'm going to coffee shop, I get a latte. and after that I'm gonna go back, right? So we need to store all these possible like transitions going from one situation to another situation. We need to store all these things and do the our optimization on this gigantic space of like possibilities.
Okay.
Okay, so it's not possible to store like all these things in the memory and like do your computation. It's like kind of not possible, and also it's like most of the algorithms we designed for in the area of like theory from the theory lens, they are we always, not always, most of the time we were like really concerned about the worst case scenario. We want to come up with the algorithm which, no matter what is the model, is gonna perform the best. Okay, so it makes almost all the algorithms we developed so far, makes all of them such that they are the best for worst case scenario. Because they want to provide a theoretical.
Right.
Why this is the case? This is the case because we are going to provide theoretical guarantee, right?
Right.
When I say this algorithm for sure works, it means that for no matter what is the world, what is the environment, it should work, right?
But that doesn't mean it's practical for any given sense. Right.
Exactly. Those are like the algorithms that they give you bounds and they give you like theoretical proof that they are gonna work. Okay. Mm-hmm. But the thing is, if you know that your environment is not that bad, is not the adversarially chosen, or is not like the worst case scenario ever can happen to your algorithm, then you can come up with a better and like more sensible algorithm. Reinforcement learning is kind of young. We need many more people to spend time and do and build up the theoretical analysis of reinforcement learning. So we are like the community of deep reinforcement. The community of the theoreticians in reinforcement learning is not as big as I cannot even say, like, it's like the proportion is almost getting to zero if you look at the number of people they do theory of like reinforcement learning compared to the people they do empirical study of reinforcement learning. This ratio is like super small. You cannot even see theoreticians. Which is like, it's both nice and also is like concerning. We should do both.
And so just to make sure I understand the first of the two impediments you mentioned, it is that in practically speaking, with deep reinforcement learning models like DeepQ, they make simplifications that lend themselves to practical concerns, computational concerns. And so, for example, they are looking at they're kind of rolling up the value into a single state, if you will, or element, if you will, whereas some of these algorithms that are, you could argue are more optimal, they may be looking at a wider set of observations of the state that you couldn't really operate on practically. Is that what you're kind of getting at?
So the more sophisticated algorithms, they design more sophisticated cost functions. So they're advancing the objective function that Deep Q-Network model is solving.
Mm-hmm.
So it's like they are advancing that. And the idea behind Deep Q-Network was not giving like best algorithm. Deep Q-Network came out to show that it is possible to play games. It doesn't claim that it's the best, and the aim of that work from DeepMind was not, hey, we are doing the best reinforcement learning algorithm. They just wanted to show that, hey, it is possible to use current algorithms in order to beat human, or like in order to learn simple games.
And a big part of that possibility was the computational feasibility.
They didn't care that much about like sample complexity. They didn't want to minimize the number of samples that the agent sees. They wanted, the main goal was, hey, we want to outperform like other algorithms, and we are gonna outperform other like humans. That was the goal behind the Nature paper they had. Was like, hey, this is the case that you can come up with the algorithm which does better than human in certain games. Or let's say for AlphaGo, like the Go game, you do not care about that much about the number of samples that your like Go players, like your agent sees. You just at the end wants to like win against the best Go player.
Right.
So it's like this is really important. This is really interesting to make it feasible for first time. But after that, you need to design algorithms. They do the thing that reinforcement learning actually requires. It's like reducing the number of samples, like learning better policy. So they made it feasible. The rest is gonna be like first make it better. By make it better, it means like come up with a better sample complexity, come up with a better value estimator. In the second work that I want to talk is like you can easily show that the DQN objective is actually biased objective function. So you better off not to do it if you want to be really serious in reinforcement learning. You better like do something else than Deep Q network. But if Deep Q network is the only thing you can do, just go with it. If you can't, if you're able to do better, it's better off not do Deep Q network because the cost function is easily biased and it can screw you up.
So elaborate on that. You said the second cost function?
No, in the second work that I'm get a chance to talk about here.
In that second paper, walk us through the results. So you started with looking at the cost function for Deep Q networks.
So I started to looking at the cost function at Deep Q network, and I have many friends from theory lands. They have many amazing papers and astonishing papers they analyzed back in like 10 years ago or 20 years ago that they analyzed these cost functions. That one of them is being used by Deep Q network, and they analyze these costs and they show that hey, they are biased. And also there is another work which shows that like for any function approximation method, there is a subset of problems that if you run this function approximation method, they either diverge or are biased. So it's like there is no hope that you can get a algorithm which is like you think that it can do something reasonable almost everywhere. But the hope is that they do not break like in the like simple setting. So if you look at the Deep Q network objective, it's like it minimizes two terms where you just care about one of them. The second term you don't want to minimize, but it naturally minimizes. Okay, and also it has some other issues of like it somehow looks at instead of averaging the errors, it just always looks at the maximum error and like backpropagate that maximum error, which is not the thing you want. If you have a Gaussian random variable, you don't care about the max. You care about like its mean. But the thing that the Deep Q network setting passes through its backpropagation is actually the max of the sample, which is not the thing you want. So it's kind of like biased in many, many different senses. And the question is, if it's biased, and if we know that any function approximation method can be biased or diverges, can we do anything for that? That was the question I was asking myself when I started to work on the second work, which we call it Generative Adversarial Tree Search, or in short, we call it GATS. Probably you have watched the movie Gatsby. So the name has some relation to that guy as well. But yeah, the algorithm is called GATS, and it's trying to address the fact that if I use function approximation for deep reinforcement learning, and if my function approximation is biased, can I do anything with respect to that or not?
And presumably you found that you could do something using a generative adversarial network-based approach.
Yeah, that's an interesting idea. So there's a line of research in psychology which says when human wants to make decision, it forecasts what's going to happen in the future. Or people say, imagine. I would avoid using word imagine, but I would say human. Like when I want to go to coffee shop from my office, I just imagine or forecast or like predict what's going to happen in the future, right? I can think of like going there, talking to the coffee man and order and pay and think about what I'm gonna get and come back. Like I can imagine and like think about it. Okay.
Mm-hmm.
So this is like a line of research in like psychology which says sometimes when human makes decision, human builds the model of the environment, model of the world and in that world does some analysis. It's not always human does analysis based on just observation. When human interact with the environment, with the world, it has some model of like some abstract model of the environment and the world in his or her brain. Okay.
Right.
I mean, maybe it doesn't make sense, but I think to me it makes sense because when I'm gonna do something, when I wanna plan for future or for my a trip, or I wanna do a road trip, I plan everything. I think of what's gonna happen, what are the situations, all these scenarios. I check all of them in my brain. I do not start my road trip and then see what's gonna happen. I just plan everything. Okay. So this is a thing that they say. Of course, there are like many decisions we do not plan for. Like let's say there's a mosquito, it just bites us. Like we do not plan to just scratch that part of the body. It just happens. So, but part of it happens through this planning, through like the model of the world that we have in our brain. So we were saying like, so let's get some idea from this part of psychology and also see what theory tells us. Theory tells us that function approximation can be biased or diverse. Okay. So now if I have a, let's say, bias like value function, okay, and if I want to use it, and also if I'm able to learn the model dynamics, the way model works, I can build the model of the world, right, in my brain. Or somehow the agent can, based on interaction the agent has with the world, here by world I mean, let's say, Atari games, given interaction that the agent has with the Atari games, going left, right, up, shooting, that kind of things, it can learn that given the current situation, if it does some sort of sequence of like decisions, what's going to happen in the future. So in this work, we use an interesting framework out there, which is called Generative Adversarial Networks. These methods, they are like used to generate images out of like random noises. So they are like kind of generative models, and we use this machinery to be able to make ourselves able to like come up with a model of the world. So now, given the samples, we designed an algorithm and a neural network which is like able, given like current frame of the Atari game, is able to tell you what is gonna be the next 20 frames. If you follow up, down, down, up, up, some sequence of actions, it's able to tell you what actually is gonna happen in the future, which is quite interesting. So if I am able to see like 20 steps from now, okay, then I can say, hey, whenever I'm gonna make a decision, I just see all possibilities from now in 20 steps in my brain, and then in the leaf nodes, so it's gonna be, I'm gonna construct a tree. I say, hey, if I am at the current time step, if I am my agent, my Atari agent is at some location in the game. If it choose action up, where it's gonna go? If it choose action down, where it's gonna go? If it goes forward, where it's gonna go? So I can ask this generative model, we call it generative dynamic model, as a short, like GDM. I can ask GDM, hey, if I am at this current state, and and my action is going up, what's gonna happen? And GDM tells me, you go to the new place. And I ask GDM, hey, now if I'm in this new place, if I go action down, where I go? So I can build up a tree for different possible actions and see where I go.
It sounds like, I mean, in a regular DRL type of problem, you're also kind of evaluating the expected reward for each of the possible actions, but that the notion of expectation is like you've lost a lot of information. And so is the idea that by using GANs to project the future state instead of, or an expectation, you retain more information?
Okay, that's actually a great point. Is if I run my DRL algorithm to compute this value, what I'm claiming here is that value can be really, really off. It means that can be arbitrarily bad. Okay, so if I run Deep Q-Network for, let's say, game Pong, for a given situation, the Pong agent, if I run Deep Q-Network, it tells me going up gives you return of like value of like 10. Okay, if I run like double deep Q network, which is another algorithm, it gives me 5. So it's like the deep Q network, the value was estimating was like off by factor of 5, by not by factor, by bias of 5 at least.
Mm-hmm.
So it's like, my point is like any deep RL algorithm can be arbitrary bias. So, and now the question is like, if it's biased, so it means that, as you said, it's supposed to tell me what is the future reward, right?
Right.
But if this estimator is like wrong, then the question is what we can do. So what we can do is like we train a generative model in order to be able to like generate future. And if I am able to generate future, you know, if I have an agent is playing in the playground and there's a ditch somewhere, and if I use this generative model and see what's gonna happen in the future, I see if I choose action up, I'm gonna fall in that ditch, right? So I do not go. So it's like somehow I'm seeing what's gonna happen in the future.
Yeah, I think maybe the question that I'm asking is, what is it about GANs maybe that allows us to be any more accurate looking into the future than the machinery used for predicting a future reward?
Okay, so it's like so we theoretically show that it's actually exponentially can improve the error in the Q function. Okay, so it's theoretically it's like exponential improvement, but practical I can tell you something. So the way we compute the way that we compute the value and return is through discount factor, right?
Mm-hmm.
So there's a discount factor. It's like the reward I get that current time step worth more than reward I receive in like next 10 time steps, right? There is a discount factor. So now if my Q function has a bias of 5, okay, and if I am able to do rollout in my generative model up to depth of 20, then the Q value I'm gonna use at depth of 20 is gonna be discount factor to the power of 20. Discount factor is less than 1, so the power of 20 is gonna be super small, times that 5. So the effect of the bias is not gonna appear. So actually this machinery has been used for AlphaGo as well. What AlphaGo does, AlphaGo is like runs Monte Carlo tree search on the board game for some depth, let's say depth of h, and when it goes to the leaf node of that tree, so it builds a tree, and then the leaf node of that tree use the learn Q value. Okay, if the Q value is biased, since I'm like rolling out for like depth of h, the effect of that bias is gonna exponentially go down. I can imagine I need to draw a tree and like explain it.
No, I think it makes sense. So the argument is that with the deep Q networks, you are predicting the future reward at a given point based on a given action, but by using GANs to project into the future what the board is going to look like, you can then discount out the errors by exactly. Because of you're predicting further into time.
That one thing is like the first part of your statement. When I use deep reinforcement learning algorithms to compute to see what is the cumulative reward of future at the given point and given action you said, my statement here is any deep reinforcement learning algorithm you use, this error in this estimation can be arbitrarily wrong. It can be arbitrarily big. So you think that you are actually learning the expected return of that state and action given that specific point at a specific action, but I can provably show that there are problems that this estimator can be arbitrarily wrong. Okay, so now I'm saying that if I had a perfect estimator, there was no need. I mean, there isn't that much of need for having generative models or GANs. But I know that this error is big for deep Q networks. These errors are gigantic, that sometimes like shockingly gigantic. People have studied this bias. We call it the bias in the estimator. People have studied these biases and they observe that these biases are like huge. It's like hundreds of percentage like bigger than the actual value.
Mm-hmm.
So it means that the estimator you get, when you compute the expected return condition on the specific point on the space and the action, that estimation can be arbitrarily wrong. Okay, so if it's arbitrarily wrong, you cannot do anything. But if it's like wrong but not super wrong, the question is, can we do anything? And one of the answers is like doing this generative adversarial tree search. Is like, if it's wrong, I can build a tree. I can look at the future and I can say I want to look at the future and see where I go after like 20 time steps. And when I go to at the 20th time step, I'm gonna use this biased value function I learned. Okay, but the thing is, whatever the value of that 20th step is, I'm gonna multiply it by discount factor to the power of like 19 or 20, something like that. So whatever is gonna be the error, that error is gonna be a squashed down exponential in depth, which is the thing I really like to have.
Are you using the GAN to predict the state only at 20, or is it 20, 19, 18, all the way down to 1, and you're discounting each of them?
I literally build the whole tree and discount all of them.
Okay. And so...
in other words, I literally build the model of the world. I literally build the MDP. If there exists MDP, right. I literally build the Markov decision process there.
Right. So a way to think about this is like you're basically trying to do what AlphaGo did with Go, but for a game like Go, you've got like fixed positions and fixed states, and while there are a lot of them, and we can't enumerate them efficiently, we know what they are given a particular state of the game now and a particular move, and we can enumerate a tree. Yeah. For an Atari game, they're more continuous. They're not like these, very discrete, moves and positions. So how do we, how might we apply this idea of getting the tree at a bunch of future states? Well, we can use GANs to do that.
Okay. There are 3 points I need to make here. First of all,
okay.
First of all is AlphaGo does this tree search on the board game, right?
Right.
And AlphaGo agent has the board game.
Right.
Has the model. But for Ataris, I do not have the model.
Yep.
So I need to actually learn the model. So there's one difference from like this GATS and AlphaGo is AlphaGo has actually the model of the environment, but for GATS, I need to learn the model of the environment.
Mm-hmm.
Second is for Monte Carlo tree search, in order to work, you do not need to have discrete like state space. They also work for continuous state space. So they guarantee like the holds for the continuous state space. So it doesn't need it. But the thing which makes it easy for Atari games is like state space hypothetically is like continuous, but the transition is deterministic somehow. It's like if I play sequence, if I choose action left, I go to left. I'm not jumping somewhere else. So it's like if we assume that this is the hypothesis. If I hypothesize that for Atari games, the state space is continuous, but still the transition is deterministic. It's like going from one state to another state. I mean, condition on the current state and my current action, I know which state I'm going to end up.
Mm-hmm.
So it makes the life of the GATS easier, but the GATS is also able to handle the stochastic state transition. If I am at the state at some frame, if I choose actually one action, if there is a distribution of going to next state, GATS is able to handle that issue as well. But generally, Monte Carlo tree search or upper confidence bound tree search, these algorithms, they do not require neither deterministic state transition nor finite state space. So they are able to handle continuous one as well.
And so one thought that occurs to me is both the question as well as thinking through the implications of the question. This process of generating this tree using GANs, what are the the computational implications of this, and assuming they're or imagining that they're significant, I wonder if maybe it makes sense to do this, like to bootstrap the deep reinforcement learning algorithm, but then once we gain more confidence, switch to something that's more like, the approach we talked about before, the Bayesian Deep Q-Networks or something like that.
Sweet. You brought up an interesting question. It's like, how hard is to do this multi-colored research?
Yeah.
How bad is the computation cost of doing this? The computation cost is bad. It makes the algorithm slow.
Yeah.
Okay.
Yeah.
But if I can get order of magnitude sample complexity, then if I'm gonna have a self-driving car, I would more compute to be able to not kill anyone. Okay.
Mm-hmm.
So here, this GATS paper, that GATS work adds like a lot of computation cost. Like I think makes it like 5 times more compared to normal DQN, normal Deep Q network. But the thing is, it's supposed to give you, first of all, better performance. Second of all, like better sample complexity. Okay. So the general thing is we use Atari games as a test bed in order to see what our algorithms are doing. We are not using Atari games. Some people they do, but I personally do not use Atari games as a competition to say, hey, my numbers are better than yours, or like my agent gets better scores than your agent, so mine is better. I'm not using like Atari games as to do this type of research, which is like probably you might not even call it research. I try to develop algorithms and test them on Atari games to see what is their behavior. Yeah, sure. Generative adversarial tree search are really bad in the sense of computation cost, but they are supposed to give you better sample complexity and also better estimation of the value functions.
Can you define, maybe formally sample complexity for me? Because for you to say that something takes 5 times as long but has better sample complexity, to me, it sounds like a contradiction in terms.
Oh, I see. So in reinforcement learning, there are like many components that you might be interested. One is like how much like wall clock hours you need to spend to find the good policy.
Yep.
Okay. So in this study, you don't care how many times you interact with the environment. You can have farm of CPUs and GPUs. All of them are playing games, and like they just give all the feedbacks to you, and you come up with a better algorithm. So if you just care about wall clock time, you don't care about the sample complexity. You just want to get to high performance in less number of hours of your wall clock.
Mm-hmm.
Okay? This study is about just engineering study. It's just about computation. So how much time you want to spend per day to be able to learn a better policy. This is an interesting line of study, but it's not my specialty, and I'm not focusing on this one. There is another one like says what objective function for DRL algorithms I can define such that I get the best policy and also get more reasonable policy and also reasonable value estimation. Okay, so there's another line of study that people have done a lot of research on it to come up with a better cost function or objective function. DQN uses the most naive objective function because the goal of Deep Q network paper was like, hey, to show that it's feasible and it's possible to outperform human or be able to run something on Atari games. So there's another line of research tries to come up with a better objective function in order to estimate better policy and also estimate better value function. Even in this case, you don't care about the number of, in this setting, you don't care about in the extreme case of this setting, you don't care about computation cost, and also you don't care that much about the sample complexity. You are like, people run the algorithms for like billions of times steps. Okay. But there's another third line, which is the most interesting part for me is like, can I get the same performance and stuff in 1 billion times of interaction with the environment in like 1 million time steps.
Mm-hmm.
So 1 million time steps is like literally so if I have two kids, they play in the Ataris and they are playing that games, I just see which one is learning faster. By learning faster, it means that the amount of hours they put to play game. If one kid is playing that game like from 8 in the morning to 9 at night, and then does better than the other kid which plays 1 hour per day, then the way I compare the smartness of these two kids somehow might be like how many hours they played exactly the game, how many hours they interact with the game, right? How many times they press up and down.
Mm-hmm.
This is going to be the notion of sample complexity. How many times my RL agent like interacted with the environment in order to get to the optimal policy.
So in other words, in this method, you may take 5 times as long to figure out each step on a wall clock, but ultimately you're able to converge to a better policy, taking less steps.
Less steps in the game.
In the game, right.
Which is actually the main goal of reinforcement learning. Is like when I deploy reinforcement learning for like autonomous vehicles, I would rather to use the whole AWS like compute to do not kill anyone, right?
Right.
So one concern is for sure compute, but main concern is like developing a better algorithm which has less number of samples required to come up with the optimal behavior.
Mm-hmm.
So this is like notion of sample complexity for this setting. I'm not using the exact theoretical notion because the exact theoretical notion has another meaning. But here somehow is like how many samples I need to. So if Deep Q-Network solves a game in 200 million samples, get some performance in 200 million samples, am I able to reach the same performance in less than 1 million time steps, less than 1 million samples? The answer in the Bayesian Deep Q-Network paper is like for some games, yes. You reduce the number of interaction you need to make with the environment 100 times less in order to get to the same performance as Deep Q-Network was getting after 200 million samples. This is the notion of sample complexity, and this is the main part of theoretical analysis in in reinforcement learning in a theory land that we mainly care about to reduce the number of samples we need in order to get to the nice and useful and reasonable performance.
And so along the same lines, can you directly compare the sample efficiency of, you said, Deep Q might be 2 billion, Bayesian, might be 1 billion. What if you throw in the GANs or GATS approach? Can you compare it directly in that same kind of metric?
Yeah, of course, I can definitely compare in the same metric. I have compared in just for one game in the paper, but as I said, since the computation complexity of GATS is a bit high, it's a bit beyond the power of academic research labs to do massive experiments. So if I was at DeepMind, I would definitely have all the games. But since I am using my advisors AWS credit, probably I rather not burn the GPU clusters we have just for this board. So I just try to show for a few games.
But for those few games, how did it compare to the other couple of methods?
Compared to Deep Q-Network, for that game we tried, it reduced the sample complexity by half. It converged to the same performance is half of the samples required for Deep Q-Network. But in order to make an empirical claim, definitely we need to try on more than, for sure, one game.
Right.
So we are trying to come up with more experiments for more games and to come up with better empirical analysis. We are not going to compare against BDQN or Bayesian Deep Q-Network because this GATS is deploying Deep Q-Network inside of it. So because I have Deep Q-Network and I'm building something on the top of Deep Q-Network, I'm going to compare against Deep Q-Network. I could use Bayesian Deep Q-Network and use GATS on the top of that, which is totally like it is one line change in the code, I could build the GATs on top of Bayesian Deep Q-Network and compare against Bayesian Deep Q-Network. This comparison is meaningful. But if I compare GATs with Deep Q-Network and compare it with the Bayesian one, is not that reasonable comparison because we are comparing two somehow orthogonal effects.
You gave the example. You said that like for a given game, you would expect that the Bayesian Deep Q-Networks is roughly half the number of samples as regular Deep Q-Networks.
No, it's like 100 times some games better.
So 100x better. And so it was this that it's the GATS that was half.
Yeah, for one game.
For the one game that you
need to run
tested.
more games. But I'm just saying something that Bayesian Deep Q-Network we studied to come up with a better exploration strategy for deep reinforcement learning problems. At GATS, we came up with the algorithm to reduce the error and bias in the learned value function. So these are kind of orthogonal effects. So the thing is, I'm not going to compare these two together because these are two studies of two orthogonal things, and I personally don't care that much which one does better because both of them can be combined together and come up with new algorithms.
Mm-hmm.
Yeah, these are like, we are in deep reinforcement learning, we are like far from claiming that we can use them in real world. So what we do, we are now like majority of the field, we are trying to study and come up with better and better algorithms. And these algorithms are like studying, because reinforcement learning like word is like too big, and we need to do a lot of study to come up with, to study different effects of different components in the setting. So we are not competing, like if in the vision community we have ImageNet, everyone tries on ImageNet and compare the results of one algorithm to another one. But here we are not doing, I mean, many people, they do compare their numbers, but I personally do not compare my numbers to say this is better than the other. We are just studying the effects of different components in the environment, and we are just in the baby stage of like reinforcement learning. We are like getting things to see what each change would do.
Yeah.
Like it's like we are very, very far from to get to the real competition to say this algorithm is better than the other one.
So in other words, it's just kind of exploring ideas about, what levers we even have available to us to tweak if we cared about maximizing performance, but we're so early on, there's really nothing to maximize performance against. There's no ImageNet or something that someone who's building a self-driving car, they might want to take all of these different approaches and, apply them together, but that's a lot of work and that's their issue. Right.
Yeah, they're going to combine everything together. You can imagine like coming up with better exploration strategy, like Thompson Sampling. It's obvious that someone should have tried this one like 5 years ago, right?
Mm-hmm.
But no one has tried it because we are like very, very, like this is a fundamental component in the reinforcement learning algorithms, right? The exploration is like one of the most important, and actually I can say even main component of the reinforcement learning algorithms, but no one has tried this one. Why? Because we are in the early stages. We are still don't know and don't get to know like what are the fundamental components of the algorithm is. Like for ImageNet, we know mainly that we need to have these convolution layers. We need to have like a softmax output. We can use cross-entropic loss. These are the common theme that everyone uses, and it works very well. But in reinforcement learning, we don't have these all components all together. We don't know what is the best way of doing exploration and exploitation together. We don't know what is the best function approximation we should use. We don't know what is the best memory we should use. We don't know. We don't. Like we are like really, really far from making any claim. We are just really even before the baby stage. We are not even got born. Right. We were not born yet.
Awesome. Well, Kamyar, you've been very, very generous with your time. Thanks so much for taking the time to chat with me about all this stuff. It was a lot of fun, and I think folks will enjoy this and learn a lot.
I really appreciate it.
Awesome. Thank you.
Oh, thank you. Have a great day.
All right, everyone. That's our show for today. For more information on Kamyar or any of the topics covered in this episode, head over to twimlai.com/talk/177. If you're a fan of the podcast, we'd like to encourage you to visit your Apple or Google Podcast app and leave us a 5-star rating and review. Your reviews help inspire us to create more and better content, and they help new listeners find the show. As always, thanks so much for listening, and catch you next time.